I'm Clint Wixson, and this is my Project 1 for Dr. Rashidi's course, Design and Manufacturing. This project is about 5 important topics we have learned throughout this course. The first topic is the decision matrix. It is a design tool used to compare alternatives and ultimately select one of those alternatives. This is the basic layout of a decision matrix. The first step is to state the issue, which is the function that the product needs to complete. The second step is to select the different alternatives that you're going to be comparing. In this case, all the concepts need to have about the same language and level of abstraction so that one alternative isn't inherently biased toward because it's more complete. The third step is to select the different criteria for comparison. These are engineering requirements that are ultimately derived from the customer requirements. The fourth step is to develop the relative important weighting of these criteria. The fifth step is to evaluate all the alternatives in terms of how well they satisfy the criteria. The sixth step is to compute the overall satisfaction and pick the best concept. This is an example decision matrix for choosing a wheel configuration. The baseline can be an existing product or it can just be a reference of what to expect. For this decision matrix, mass efficiency and stiffness have the highest relative weight. Although not required, it is a good practice to ensure that the weights add to 100 as shown here. This is because it's easy to have all of the criteria at a high importance, and this forces a more complete look at what's actually most important. Spiral flexures have the highest weighted total, so this would be a good concept to select. If multiple concepts have a similar weighted total, it may be beneficial to investigate both further. Decision matrix can be a useful tool for engineering design, but they are limited by the information provided. Engineers may have to make an educated guess to fill out certain areas of the matrix. However, overall, the decision matrix is a good method for choosing among several alternatives and can be easily applied in other contexts. The next topic is reverse engineering, which is a design tool used to understand existing products. The goal of reverse engineering is to understand the function and flow of energy, information, and materials of an existing product. After investigating the product as assembled, it is decomposed into individual parts. These parts are analyzed in terms of how they connect and function within the assembly. They are measured and documented for possible recreation. Applications of reverse engineering include legacy part replacement, which is used when a manufacturer has discontinued a certain part. It can also be used to conduct failure analysis and figure out how to improve upon the product. Service and repair shops also use reverse engineering to understand how the product works in order to learn how to extend its life or fix it when it breaks. Reverse engineering has several limitations. One is that the engineer must physically have the product in order to reverse engineer it because they have to measure and interact with the product. Complexity can also be an issue because it makes the product more difficult, time-consuming, and costly to reverse engineer. Reverse engineer can sometimes produce inaccurate data due to imprecise equipment or incorrect procedures conducted by the engineer. Patent issues can also arise from reverse engineering if directly copying ideas from competitors. One quote I found is, "Copying from one is stealing. Copying from many is research." The next topic is shot peening. Shot peening is a manufacturing technique that treats the surface of a part. Shot peening works by impacting the surface of the part with shot, which are small balls. The shot is typically made of cast steel, glass, or ceramic, and are 0.125 millimeters to 5 millimeters in diameter. The shot makes small indentations on the surface by plastically deforming the part. This causes the part to have residual compressive stress. This stress improves the fatigue life of the part by slowing down crack propagation. In the best cases, shot peening can increase fatigue life by 1000%, although this depends on factors like shot quality, material, intensity, and coverage. Shot peening is used on many parts that are constantly or nearly constantly spinning or moving. This is because these parts are particularly susceptible to fatigue. Some examples include valves, gears, camshafts, springs, propeller shafts, turbine blades, and compressor blades. The improvement of fatigue life outweighs the cost of shot peening for these applications. The main limitation of shot peening is the cost. Shot peening is a surface treatment and is usually conducted after all machining is complete. This means that is an additional cost due to an additional process. However, if the part is likely to fail in fatigue, shot peening can save money in the long run by prolonging the life of the part. Shot peening can also reduce the tolerance of a part. However, this is mitigated by using fine particle shot peening in high tolerance cases. The pebbly surface created in shot peening process can be undesirable in certain situations. The next topic is die casting. Die casting is a commonly used manufacturing process for metals. It was developed in the early 1900s. Die casting is a permanent mold casting process, meaning the mold or die can be reused. This process works by using a ram to force molten metal into the die cavity. The metal is held under pressure until it solidifies and is released. This image shows a cold chamber die casting process, which is used for materials with higher melting points. There's also a hot chamber die casting process that is used for materials with lower melting points. Die cast parts can hold to tight tolerances, especially when using high quality molds and dies. This process can also produce complex details, including inserts and thin walls. Because the process is highly automated and the parts need little to no finishing operations, the cost per part is low for high volume runs. Die casting is used in a wide variety of applications. Engine components such as blocks, cylinder heads, and housings can be made using this process. Kitchen appliances, both power and hand tools, as well as many different toys, are die cast. One of my favorite toys from my childhood, Hot Wheels cars, are made using the die casting process. The high cost of dies and die casting machines can be a major limitation. This means die casting is not suitable for parts that have a low volume production. However, in high volume production, the cost for the die can be amortized over thousands of parts, offsetting these high initial costs. Also, only non-ferrous metals with moderate melting points can be die cast. Die cast parts are also susceptible to defects such as drags, blisters, and cracks. The last topic in this video is CNC Incremental Forming. CNC Incremental Forming is a relatively new sheet metal manufacturing process. The CNC incremental forming process uses a rotating tool to apply localized pressure to a stationary blank of sheet metal. This results in a progression of deformation that produces a desired shape. CNC incremental forming can be used to produce complex parts that may not be possible using traditional sheet metal forming processes. Because the process does not rely on dies or other machinery specific to each part, CNC incremental forming has low tooling costs and short lead times. This makes the process great for prototyping and small batch manufacturing. CNC incremental forming has a low production rate due to its slow, progressive process. This makes it unsuitable for repeatedly making the same part, such as in high volume production. Another limitation is the materials that can be used with this process. CNC incremental forming works best with aluminum alloys that have a high formability. However, it's also been shown to work with copper and brass. Current research into this process may improve its viability for use outside of prototyping and specialty parts. This video covered the decision matrix, reverse engineering, shot peening, die casting, and CNC incremental forming. Knowing how to use a decision matrix is valuable because it allows an engineer to make an efficient choice between different alternatives. Reverse engineering is important because it allows existing designs to be investigated. Things learned in reverse engineering can be used to help inform future designs as well as to replace existing parts. The surface treatment and manufacturing processes included in this video are important because it allows an engineer to design products with these processes in mind. Shot peening can be used if an engineer is worried about the fatigue life of a part that they are designing. Die casting is a good choice for metal parts that will need a high volume run. CNC incremental forming is useful for prototyping sheet metal parts, and future improvements may make this a more common process. These are the references I used in creating this video. The main references are the two textbooks used in this class, the mechanical design process with case studies, and manufacturing processes for engineering materials. I also used some websites to further inform this video, including what is reverse engineering and how does it work, take apart a household appliance, reverse engineering explained, methods and uses. I also used what is shot peening and how does it work, stainless steel shot peen pipe, what is die casting, processes, materials, applications, cost, and 13 die casting defects and how to avoid them, and finally, incremental forming. Thanks for watching this video. I hope it was informative and will help make you a better engineer.